Hello, Algebra 2. Well, I hope you thought last week was pretty straightforward and easy, and I think I warned you that it was going to get more complicated. Here it comes. I apologize now, this slideshow is going to be a little bit long. The good news is this is the last we have to say about logarithms. So after this week, we'll be moving on to Unit 10. Here's our objectives for the week. You can read them for yourself. So if you'll join me on slide 2, we will get right into it. So to introduce you to log properties, I'm going to start by asking you to try to evaluate these logarithms. You should be able to do this without a calculator if you would just think carefully about what logarithms are, what they represent. So we'll remind you that on problem 1, this is the common log, and so we're asking the question 10 to what power equals 10, and the answer is 1. The second question is asking you 10 to what power equals 100. That would be 10 to the second power. And the third question is 10 to what power is 1,000, and that would be 10 to the third power. On question 4, we've changed to log base 2. So now we're asking you 2 to what power is 2? Again, the answer is 1. Then we're asking you 2 to what power is 3? Excuse me, 2 to what power is 8? The answer is 3. 2 to the third power is 8. And finally, 2 to what power is 16? And that would be 4. So if you've got those answers, the next thing we would ask is, do you notice anything about those problems and about those answers? So looking at the first column, some people might say, oh, well, the answers are in order 1, 2, 3. But maybe if you look at the second column, maybe you'll see something different. The answers are 1, 3, 4. Those aren't necessarily in order. But if you took some time and thought about it, I would hope that eventually you might notice that, hey, the first two answers add up to the second answer. In other words, 1 plus 3 is equal to 4. And actually, the same is true with the first three problems. 1 plus 2 is equal to 3. Here's another way of looking at those same problems. Here are the first three problems we gave you, and there are the second three problems. And then below them, there are the answers to each of the logarithms. As we pointed out before, the answers add up. 1 plus 2 is equal to 3, and 1 plus 3 is equal to 4. But here's the other thing that we didn't point on the last slide. Look at the questions. 10 times 100 equals 1,000, and 2 times 8 is equal to 16. And so the question is, down at the bottom, does this always work? If you have log of A plus log of B, does it always equal the log of A times B? Notice in the first set of problems it was log base 10, and the second set of problems it was log base 2. So it doesn't seem to matter what the base of the logarithm is. Does that pattern always hold true? Well, the answer is yes, and here's an explanation of why. What we've done now is we've rephrased each of the questions a little bit. I hope you, on the first set of problems, 10 is 10 to the first power, 100 is 10 squared, and 1,000 is 10 cubed. So I'm just rewriting the questions as all powers of 10. And similarly, on the second set of questions, 2, 8, and 16, those are all powers of 2. So 2 is 2 to the first power, 8 is 2 cubed, and 16 is 2 to the fourth. Well, when you look at it written this way, I hope it starts to make more sense to you, because take the first row, for example, 10 cubed. Well, 10 to the third power is really 10 to the 1 plus 2. And you should know that there's an exponent rule that tells you, when do you add exponents? It's when you're multiplying. When you're multiplying two expressions, that's when you get to add the exponents. And we could do the same thing for the second set of problems. You get to add these exponents when you're multiplying. Well, logarithms are exponents. Just think about what a logarithm is. Let's say, for example, if we were to ask you, what's log base 2 of 8? This is asking you 2 to what power is 8? See, this answer that you just got represents an exponent because you're saying 2 to the third power is 8. So logarithms really are just another way of expressing an exponent. And you already know, or you should know, that there are rules that allow you to add exponents, multiply exponents, and subtract exponents. Now, we just showed you an example using one of the exponent properties that you should know. Here are all the exponent properties you should know. These all come from the prior unit. So if you know that there are properties that tell you here's a situation where you get to add exponents, here's a situation where you get to subtract exponents, and then here's a situation where you get to multiply exponents. Well, if you have rules that tell you you get to add, subtract, and multiply exponents, and if you understand that logarithms are just exponents, then I hope it doesn't come as too much of a surprise that we have rules about adding, subtracting, and multiplying logarithms, because logarithms are exponents. So here they are. These are the 3 basic log properties that are a direct consequence of the exponent rules that you should already know from the prior unit. I'd just like to point out on this slide that the base of the logarithm doesn't matter. All of these are written as log base b. We don't care if the base is base 10, like the common logarithm, base 2, could be base e, which is the natural logarithm. These log properties work no matter what the base is. So there's the log properties, and let's take a look at how we could put these properties to use. So here's a few problems to just give you a simple illustration of how you could use log properties. Log 4, and that is the common log. Common log of 4 is 0.602, and the common log of 12 is 1.079. Now those are rounded answers, those are not exact, and I got those from a calculator, so if you want to get a calculator and check me, you can. But if we told you that log of 4 is 0.62 and log of 12 was 1.079, how could you, without using a calculator, figure out what's log of 3? So this is an example of how we could use log properties. What we would need to do is first recognize that, okay, wait a minute, 3 is 12 divided by 4. So that's the first step. Now, why would I do 12 divided by 4 instead of 6 divided by 2, let's say? Well, the reason I want to use 12 and 4 is because those are the logarithms that you've given me the values of. See, with log properties, I know that log of 12 divided by 4 is log of 12 minus log of 4. In other words, this is 1.079 minus 0.602, which means this logarithm should be equal to 0.477. Now again, keep in mind that's a rounded answer. All of these numbers we're dealing with have been rounded to the third decimal place, so it's not exact. But I invite you to get a calculator or use Desmos and find the common log of 3, and you're going to find that common log of 3 is approximately 0.477. So let's clear the slide and take a look at the second one. How can we figure out the common log of 48? Well, it's a similar exercise. First step is to recognize that 48 is just 4 times 12. Again, the reason I'm using 4 times 12 and not 24 times 2 is because of the logarithms that you gave me in the problem. So this is, according to my log properties, this is the log of 4 plus the log of 12, which means it must be 0.602 plus 1.079. And so the common log of 48 is 1.68. 1. And again, I invite you to use a calculator and check that answer. Okay, we'll clear the slide for one final example. How could we find the log of 16? Now, you might be thinking to yourself, oh, I know, 16 is 4 plus 12. Well, that's true. 4 plus 12 is 16, but I'm not sure how that helps us. We don't have any log property that we could use in that situation, so that's actually not going to work or not going to get us an answer. So I'm going to erase that. Now, the better way to do this would be to recognize that, hey, 16 is 4 squared. Now, that we have a property for because that 2 can come down and become a coefficient, and log of 4 is 0.602, so we now know that this is 1.204. So that just gives you an idea of how you can put these log properties to use. And on the next slide, we'll have a few more examples. Okay, so on these problems, we want to use log properties to try to write each one of these expressions as a single logarithm. For these problems, I've taken each problem and put it on its own slide. So join me on the next slide and we'll work through problem 1 together. Okay, so how do we write log base 2 of 4 plus log base 2 of 8 minus log base 2 of 64 as a single logarithm? Well, if we use our log properties, we should know that the first thing we could do is whenever you're adding two logarithms, that would be the log of 4 times 8. In other words, that would be the log of 32. Now you still have this other logarithm, and now we're subtracting logs, so we should know that there's a property that says, well, you get to divide those numbers. That's 32 over 64. In other words, you are taking log base 2 of 1/2. Now, let's take a second and go one step further. What is log base 2 of 1/2? This is asking the question, 2 to what power is 1 over 2? Well, hopefully you remember that that's what a negative exponent is. This logarithm would be equal to -1. First of all, this is the answer to the question, because the question asked to write this as a single logarithm with no leading coefficient. So that's the answer to the question. The only reason that I evaluated it as -1 is because I just wanted to give you some confirmation that you've done this problem correctly. Because what if we went back to the original problem and just evaluated each of the logarithms? What is log base 2 of 4? This is asking 2 to what power is 4? Well, 2 to the second power is 4. How about this next logarithm? Log base 2 of 8 is asking you 2 to what power is 8? Well, that would be 3. And then the final question is asking you, the final logarithm is asking you, 2 to what power is 64? Now, you might have to write that one out on paper for you to get the answer, but 2 to the 6th power is 64. Now, don't forget, you were supposed to be adding the first two logarithms and subtracting the last logarithm. So what's 2 plus 3 minus 6? Well, it's -1. So you can see that we definitely got the right answer when we wrote our log base 2 of 1/2, because both of these problems equal -1. Let's look at problem 2 on the next slide. So this problem has been designed to point out something that you need to be careful with when using log properties. And to emphasize that point, I'm going to do this problem incorrectly the first time. So please take note that this is the incorrect way to do this problem. Okay, so we are subtracting two logarithms. So according to the properties, we should be able to divide, and that would be 4 divided by 2. 4 divided by 2 is 2, and we could say that we have a single logarithm now, but this single logarithm has a leading coefficient, and we are not supposed to have a leading coefficient. So there is one more log property that we could use, and that leading coefficient become an exponent. So you can see that this is log base 4 of 4. At least that's what we think, but I already told you we've done this problem the wrong way. Now, how can I confirm that this is the wrong answer? Well, let's evaluate that logarithm, just like we did on the previous example. 4 to what power is 4? I hope you know that that answer is 1. Let's go back to the original problem and try to evaluate the logarithms. Um, the original logarithm, log base 4 of 4, that's just the same thing we asked. 4 to what power is 4? The answer is 1. But that logarithm was supposed to be multiplied by 2, so don't forget you have a 2 there. Now, what about this logarithm? This is asking you 4 to what power is 2? Well, 2 is the square root of 4, so that would be a half. And you're supposed to be subtracting those logarithms, so I hope you can see that the correct answer would be 2 minus 1/2. In other words, the correct answer should be 3/2, and that's definitely not what we got. So this is the incorrect way of doing this problem. The question is, what did we do wrong? Well, I'd like to point out to you in the very first step, the first thing you did was you subtracted the two logarithms and you used the property to rewrite that subtraction problem. That means you basically violated the order of operations. I'm going to clear the board so that we can see the problem clearly again, and now we'll do it the correct way. Just don't forget that the answer we should be getting is 3/2. Okay, so as I said, the mistake you made is you violated the order of operations because you did the subtraction before the multiplication. You're supposed to multiply by 2, and you should know, according to PEMDAS, that multiplication comes before subtraction. So the correct thing to do would be first take care of that exponent, because that's what the 2 is. The 2 is really an exponent. So that's really log base 4 of 16. Now you can do the subtraction. And the subtraction means you have to divide. So 16 over 2. This is the log base 4 of 8. So there's the answer to the problem, because now you have a single logarithm and it has no leading coefficient. But what about confirming that that is the correct answer? Well, remember we said that this question should come out equaling 3/2, right? How do you evaluate log base 4 of 8? Well, this is asking you 4 to what power is 8? And remember back in the prior unit, we showed you how to answer questions like this by getting a common base. 4 is 2 squared, and 8 is 2 to the third power. And I get to multiply these two exponents here, so that's 2 to the 2x. And if 2 to the 2x equals 2 to the third power, then that means 2x has to equal 3, which means the answer is 3/2, which is what we knew the answer should have been. So now we did it the right way. Okay, here comes our third and final problem, and once again this problem has been created to illustrate something you need to watch out for. So log base 4 of 64 minus log base 2 of 1/2, we're subtracting two logarithms, so your first inclination might be to divide 64 by 1/2. But the question you might have already thought of is, wait a minute, what's the base of this logarithm? Because one of the logs was log base 4 and the other was log base 2. So should this be log base 4 or should this be log base 2? Well, that's the other thing we wanted to point out. If you go back and look at the log properties, we said we didn't care what the base was, but the base does have to be the same within the property. So if you go back and look at your log properties, the base can be whatever you want as long as it's the same base in the entire problem. This problem, you don't have the same base. So you can't use log properties, at least not right now. So the takeaway from these last few examples were make sure you follow the order of operations. You always have to respect the order of operations. And make sure you've got the same base. If you don't have the same base, then you can't use log properties. Okay, well, that problem of not having the same base, that leads us to one final property you need to learn. And for this one, we want you to think about this question. 3 to the x equals 20. We're just giving you that as a problem. Now, look at the second line. Imagine we were taking the log of both sides. And in this problem, we're going to do the natural log. So if 3x is equal to 20, then it stands to reason that the natural log of 3x must equal the natural log of 20. Now, on the third line, we're using one of the properties we just taught you. You can take an exponent and turn it into a leading coefficient. So x times the natural log of 3 equals the natural log of 20. And to get to the last line, all we've done is divide both sides by the natural log of 3. So you can see x must be the natural log of 20 divided by the natural log of 3. Okay, now why are we doing this? Well, go back to the very first line, 3 to the x equals 20, and think about what that exponential statement would be if we wrote it as a logarithm. 3 to the x is equal to 20 would be equivalent to log base 3 of 20 is equal to x. In other words, that logarithm is saying 3 to what power equals 20, and that's exactly what the second line is saying. 3 to the x equals 20 is asking 3 to what power equals 20. Okay, well now look at the first line and look at the last line. If log base 3 of 20 is equal to x, and if x is also the natural log of 20 divided by the natural log of 3, then doesn't that mean that the log base 3 of 20 is the natural log of 20 divided by the natural log of 3? Now here's the really crazy part about this. In this problem, we took the natural log of both sides of the equation. My question is, what if we didn't take the natural log, but we took the common log? Or what if we took log base 2 or log base 5 or whatever log you want? It really wouldn't change anything except it would change what's the base of the logarithms in the fraction. Since we took the natural log, that's why you have natural log of 20 over natural log of 3. If we had taken the common log, we would say it's the common log of 20 over the common log of 3. This gets us to the last and frankly what I think is one of the most important properties. This is called the change of base formula. What we're saying here is that if you have a logarithm with base c, you can rewrite that to be log base b of a divided by log base b of c. The important thing to notice in this formula is notice that the logarithm now has a base of b, and b was not anywhere in the original problem. So that means b can be any number you want it to be. It can be the common log, the natural log, log base 2, log base 4, whatever you want. This is why we call it the change of base formula. You're changing a problem from a base of c to whatever number you want it to be, which is a pretty powerful and convenient thing to do. So let's take a look at this problem that we said a minute ago we couldn't do because they had two different bases. There's no way to use log properties right now because these don't have the same base. Well, you can change the base. Let's try changing it to base 2. If we want to change it to base 2, then you don't need to change that logarithm. It already is base 2. So how do you take this logarithm and write it as base 2? Well, that would be log base 2 of 64 divided by log base 2 of 4. Now, what is the log base 2 of 4? This is saying 2 to what power is 4? Well, I hope you realize that that is 2. So log base 2 of 64 over 2. Now, dividing by 2, that's the same as multiplying by 1/2. And remember, leading coefficients can be thought of as exponents. And don't forget, raising to the 1/2 power is the same as taking the square root. So we just found out that that first logarithm is equivalent to log base 2 of 8. And now notice, now you've got two logarithms with the same base. And since they have the same base, now you can use the log properties. So this is 8 divided by, that was 1/2. And 8 divided by 1/2 is 16. There's your single logarithm with no leading coefficient. So now for the last little bit of our slideshow, and I know this has already been a pretty long one. We want to go back and we want to look at how we could actually use logarithms as an algebraic operation. In other words, how can we use them to solve problems algebraically instead of solving by graphing or doing something else like that? This is a problem that we presented in last week's lesson. Log base 2 of x minus 1 equals log base 4 of x plus 1. And we said that we couldn't solve this using the one-to-one property. We couldn't solve it by rewriting in its exponential form. And the problem was that the base does not match. You had log base 2 and log base 4. Well, I hope you now understand this is one reason why the log base property is so important. If you want the bases to match, you can change the base. Let's change everything to log base 2. So we're going to leave this one alone because it already is log base 2. And to change the other side to log base 2, we would say log base 2 of x plus 1 divided by log base 2 of 4. Now, log base 2 of 4 is 2. And now we got to get rid of this 2 before we can solve the equation. So let's multiply both sides of this equation by 2. Okay, that means you're going to have a 2 over here. And on the other side, the 2 goes away. Now, we have to get rid of the 2 as a leading coefficient, so we have to use our log properties to turn it into an exponent. And now you're in a position to use the one-to-one property. You have log base 2 of x minus 1 squared equals log base 2 of x plus 1. Since they're both log base 2, we can basically ignore the logarithm. And now all we need to do is solve x minus 1 squared equals x plus 1. So let's clear the board and finish that. Okay, so we had x minus 1 squared equals x plus 1. X minus 1 squared would be x squared minus, don't forget to FOIL that, so it's x squared minus 2x plus 1. And now we're solving a quadratic, so I hope you remember that you should make this equal to 0. So if I subtract x from both sides, this is going to turn into that. And if I subtract 1 from both sides, then the 1 just goes away. Now you have a quadratic that's equal to 0. Well, that quadratic can be factored. Remember, first kind of factoring you should always do is greatest common factor, and the greatest common factor is x. If you factor this, I hope you can see that the answers are going to be x equals 0 or x equals 3. So it looks like this problem has two answers. Except, don't forget, whenever you solve a log equation, you have to be mindful of the domain restrictions. This answer doesn't work. And why doesn't it work? Because if you plug it in, you would be doing log base 2. 0 minus 1 is negative 1. You can't do log base 2 of negative 1. Negative 1 is not part of the domain of that logarithm. This is what we would call extraneous, something that we haven't had to worry about in a while. That answer doesn't work. But this answer does. I'm going to clear the board, and sorry I changed colors and forgot to change back. We're saying that 3 is a valid answer. So if we try to plug that answer in, you can see log base 2 of 2 is equal to log base 4 of 4, and that is a correct solution because both of those logarithms are equal to 1. So let's take a little closer look at what we mean by using logarithms to solve things algebraically. Let's take a step back and talk about solving in general. If you try to solve the equation on the right, hopefully I hope you can solve this equation without too much trouble. Some things you should already know about solving. So I hope you know that you've got to follow the order of operations, but I hope you also realize that what you're doing when you solve is you're using the inverse. You're doing inverse operations, and that's how you make things go away. Some of you guys call it doing the opposite. Why did we subtract 5 here? Because subtracting 5 is the opposite of adding 5. Why did we divide by 2 here? Because dividing by 2 is the opposite of multiplying by 2. So you were doing the opposite to make things go away, to isolate the variable. Well, the opposite is really just another word for the inverse. Subtracting 5 is the inverse of adding 5. Dividing by 2 is the inverse of multiplying by 2. What you have to understand is logarithms are the inverse of exponentials. So if we wanted to solve an equation like the one on the right, now that's an exponential equation, and in the prior unit we taught you to solve it by finding a common base. But let's talk about how could we solve it with a logarithm now. Well, you still have to respect the order of operations. So the first thing I would do is get rid of the 3. And now when you get to this point, instead of thinking of this as finding a common base, try thinking of it this way. You're trying to solve for this variable. To get that variable by itself, you have to get rid of this 2. Now, how do you get rid of that 2? Well, that's an exponential function with a base of 2. So what would the inverse of that be? Well, it would be the log of base 2. So what we're going to do is we're going to take log base 2 of both sides. Now, the logarithm base 2 is the inverse of the exponential base 2. And whenever you do a function and its inverse, they cancel. And so what happens is the left side leaves you with just x plus 4. Now, on the right-hand side, you have a logarithm that you can evaluate. 2 to what power is 8? Well, that's 3. And if you just subtract 4 from both sides, you get the answer. You've isolated the variable. Here's some problems that you already solved in the previous unit. When you solved these problems last time, you did it by finding a common base. But let's take a look at these same problems again, except we're going to do it by using logarithms to solve. The first problem is very similar to the one we already solved, so I'm going to start with problem 2. 3 to the x minus 2 is equal to 7. Again, think about the order of operations. The first thing you should do is move the 2. Now you've got 3 to the x is equal to 9. Okay, you have an exponential with a base of 3. So what's the inverse of that exponential? Well, the inverse of an exponential with base 3 is a logarithm with base 3. So you need to take log base 3 of both sides. Again, log base 3 is the inverse of an exponential with base 3, so those things cancel out, and now you're just left with x is equal to log base 3 of 9. This logarithm is asking 3 to what power is 9, and we know the answer is 2. Let's clear the board and take a look at the next problem. This was a problem that we said couldn't be done by common bases. So if you take this problem and think about the order of operations, the first thing you should do is move the 3. The next thing is divide by 2. And now you're ready to use a logarithm. You have an exponential with a base of 1/2. So you're going to need to take log base 1/2 of both sides of this equation. Log base 1/2 is the inverse of the exponential with base 1/2. So those cancel. And that means you've isolated the variable, and the answer is log base 1/2 of 3/2. Now, if you were trying to get a numerical answer, how do you do log base 1/2? Well, if you have a calculator with the log base command, you can do log base 1/2. But if you don't have a calculator with a log base command, if you know the change of base properties, you could find that logarithm by just use the natural log button, because that's the natural log of 3/2 divided by the natural log of 1/2. And if you punch that into a calculator, I think you'll see that the answer you get is negative 0.585, which is the same answer we got when we did this problem by graphing. This is another problem that you guys already solved before in the prior unit, so I'm going to go through part A quite quickly. If I wanted to write a function that would represent the value of the car, I could do it by writing this equation here. And for the second part, you want to know how long will the car be worth more than $10,000. So if I put 10,000 in for the value of the car, I'm basically asking you to solve for x. Okay, so if you think about order of operations, the first thing you would do is divide both sides by 15,000. And now you have an exponential with a base of 0.95. So that means it's now you can use a logarithm to get rid of the exponential. 10,000 over 15,000 is 2/3, so we can rewrite that to make it a little more simple. All right, so if you take log base 0.95 of both sides, then on the right-hand side, log base 0.95 and the exponential with base 0.95, the logarithm and the exponential will cancel because the bases match. And so you've got log base 0.95 of 2/3 equals x. That's your answer. Once again, with the change of base property, in case you didn't have access to a calculator that could do log base 0.95, you could evaluate that logarithm by doing what's the common log of 2/3 divided by the common log of 0.95. And then you would have a numerical answer. Here's just a little more trying to make sure you understand the relationship between logarithms and exponentials. In this unit, we've been solving log equations. We solved equations with a single log or equations with 2 logs. How could we solve these thinking about this exponential relationship? So this is a little more awkward to talk about. Here you have a log base 3, and on the left-hand side, sorry, if you want to make this log base 3 go away, then you need to do an exponential function with a base of 3. So what I'm doing is taking the entire left side and using it as an exponent with a base of 3. And that means I have to do the same thing on the right-hand side, use it as an exponent with a base of 3. Now, exponential with a base of 3 and logarithm with a base of 3 are going to cancel. And so what you've got here is just x plus 5. And 3 to the third power is 3 times 3 times 3, which is 27. So now you can see how using the exponential helped me isolate the variable. So on the second problem, we can do a similar sort of thing. Both of these are log base 2. So if we would just think of it as take the left-hand side and turn it into an exponent with a base of 2, do the same thing on the right-hand side, make it an exponent with a base of 2. Once again, you have an exponential with a base of 2 and a logarithm with a base of 2, except this time you have it on both sides, which means they're going to cancel. So x is equal to 2x minus 4, and now you can finish solving. So I hope you are now starting to understand the way logarithms and exponentials are inverses of each other and how you could use them to go about solving equations. Here's one final problem we want to look at and try to help you put this all together. Here we have 3 logarithms. They're all base 2. I'm going to work this the wrong way as to illustrate a point again. If you think about the one-to-one property that we taught you before, you cannot just ignore all of the logarithms. You cannot look at this and say, oh, well, they're all log base 2, so let's just pretend the logarithm went away. Because if you did that, then you would end up with this, and that's saying x plus 1 equals x plus 3. And if you try to isolate the variable, when you subtract x from both sides, you end up with this perplexing result. Now, you've had something like this happen before in our class, and when something like this happens, it sometimes means that there is no solution. So does this problem have no solution? No, this problem does have a solution. So let's back up and do it the right way and try to help you understand what you did wrong. First of all, if you were trying to do this with the one-to-one property, you can't do that when you have 3 logarithms, or you can't do that when you have more than one log equal to another log. So if you wanted to use the one-to-one property, the first thing you would need to do is put this together into a single logarithm. Now, with log properties, you can do that. Those are both log 2, and according to the log properties, that means you are allowed to multiply those two expressions. So that means this is log base 2 of 4x minus 12. Now you have a single logarithm that's equal to a single logarithm. Now you can use the one-to-one property, which basically says I can just ignore these logarithms. So if 4x minus 12 is equal to x plus 3, then that means 3x is equal to 15, or in other words, x is equal to 5. And if you go back and look at the original problem, because remember you want to make sure you're not violating any of the domain rules, we can plug in 5 here. We will not be taking the logarithm of a negative number, and we can plug in 5 here, and we also will not be taking log of a negative number. So that is a valid solution, and that's an example of how you can use log properties to then put you in a position to where you could use the one-to-one property to solve a log equation. Okay, I apologize again. I know this was a long presentation, but we had a lot to talk about. There are 4 log properties that we taught you, and we hope you now understand what they are and how to use them. You have a property that lets you work with the sum of 2 logs, the difference of 2 logs, log of something raised to a power, and then you have the change of base property, which I think is one of the more powerful properties. Maybe not quite as important as it used to be if you have a calculator that has a log-based command, but if you have an older calculator, or if you just have a scientific calculator and all you have access to is the common log or the natural log, that change of base property is really handy because it lets you evaluate any logarithm with any base. And then the last thing we did is we talked a little bit about how you can use logarithms as an operation. Logarithms are the inverse of exponentials. And if you understand that, you should be able to use logarithms to help isolate variables when you're solving problems. This week, for checking your understanding, we're going to have 2 separate assignments, and it's important that you understand the difference between these 2 assignments. The first one is going to be just an assignment to check how well you understand log properties. This will be an assignment that you can submit unlimited number of times, and we want you to submit it an unlimited number of times until you get all of the answers correct. Once you get all of the answers correct, then you'll get 100 for completing the assignment. But until you get all the answers right, it's going to show up as incomplete, or it will show up as a 0 after the deadline. Now, after you take that first assessment to test your understanding of the properties, then we have a final assessment that covers the entire unit on logarithms. The final assessment is called Pre-AP Review of Logs. This covers everything we talked about on logarithms, starting with the basic definition of a logarithm, graphing log functions, solving log equations, and log properties. This assessment you don't get to do an unlimited number of times. You only get to submit it 3 times. You will, each time you submit it, you will get feedback. You'll be able to see which questions you might have gotten wrong. And then the idea is when you try it the second or the third time, you hopefully will correct the mistakes and get the problems right. After 3 attempts, though, you won't be able to do it anymore, and this is not going to be an automatic 100. Your grade is going to reflect to what extent you got the answers right or wrong. So try the log property assignment first. Do it however many times you need to make sure you get all of the questions right. Then review everything we've said about logarithms going back to the very beginning, And then when you think you're ready, try the final assessment on pre-AP review of logs. If you've got questions or you need help, join me for office hours every day at 1 o'clock, and either through the discussion board or by email. And that's it, folks. The next presentation next week will be the start of Unit 10, our final unit of the year. Good luck.